So we'll get into some more details about those subatomic particles. Sub is a prefix meaning below. So these are particles that are smaller than an atom in size. All atoms have the same subatomic particles in them, just varying numbers of those particles. So those particles are protons, neutrons, and electrons. In this slide, we're given the actual masses in kilograms of these particles. You might have to refer to that occasionally for a homework problem. I do not expect you to remember that. I would like you to remember that they are really, 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 really small. Okay, 10 to the minus 27 kilograms. If we compare those masses, we see that the mass of the proton and the mass of the neutron are virtually the same. They differ in the fourth significant figure, so we can think of them as being the same mass. The mass of the electron is much, much smaller. A visual on how big the electron is relative to the protons. If the proton was a baseball, then the electron would be the size of a grain of rice. So much, much smaller. You think about an atom, and the smallest atom has one baseball in the middle and one grain of rice floating around. Larger ones could have, 10, 20, 30 baseballs. Now we're getting pretty big in the middle there, or even more, and then that many number of grains of rice floating around. So the kilogram, even the gram, even a nanogram, picogram, these units are not well suited for measuring the masses of extremely small particles. We like to have a unit that is similar in size to what we're measuring. And all of our metric units are just way too big to measure subatomic particles. So we made up a unit, which seems a little flip, doesn't it? But where do all units come from? They are all made up, right? The inch, the foot. Oh, well, those are regular things, yeah. Because at one point in history, somebody made it up, right? So we made up another unit just because we needed one. Very creative title here, atomic mass unit. It's used to measure the mass of atoms. The definition here seems a little odd. And they actually just redefined some of the metric units. So I'm going to acknowledge that, but that's not in the slides, and it actually doesn't matter for our purposes, so we're going to pretend that didn't happen. One atomic mass unit was originally defined as 1/12 the mass of a carbon atom containing 6 protons and 6 neutrons. So it was defined relative to a carbon-12 atom. The carbon-12 atom has a mass, and they say, well, the atomic mass unit is 1/12 of that. So that means that the mass of a proton or a neutron is approximately 1 atomic mass unit, because a carbon-12 atom has 12 protons and neutrons altogether. So this is a useful table giving us some of the properties of subatomic particles. We're talking about mass. There's masses in kilograms. That's nice, but not really all that important. These masses are more significant. I don't expect you to remember all of those digits. You should remember that a proton has a mass of 1. Ooh, that's a very shaky one. 1 atomic mass unit. A neutron is 1 atomic mass unit. And we can think of an electron as being approximately 0. Electrons do have mass. I didn't know they were Catholic, but they do have mass. But we can usually ignore that. You guys aren't awake yet, are you? When we look at the charges, we find that the charge of the proton and the electron are equal in magnitude but opposite in sign. And so we can measure their charges in coulombs, the unit of charge. That's nice. We're not going to need those numbers much, if at all. What we are interested in are relative charges. So the proton has a positive 1 charge. The neutron, being neutral, has 0 charge. The electron has a negative 1 charge. So you don't need to remember that. You don't need to remember that. You don't need to remember that. But these things are important. Relative masses, relative charges. Okay? Any questions? So matter is generally charge neutral, meaning it doesn't have a positive or a negative charge because the number of protons and the number of electrons are equal in that matter. When matter does acquire a charge, it tends to be unstable. Nature doesn't like that separation of charge, and that imbalance will equalize often very dramatically. Lightning is an example of what happens when you get a charge imbalance. So you get a negative charge building up in the clouds, a positive charge building up on the ground, and you get this electrical discharge. Violent, dramatic, dangerous. Okay. Smaller example would be static electric shocks. You know, you shuffle your feet on the carpet and then you touch a metal door jamb and you get a little shock. It doesn't happen as much here because it tends to be a little bit more humid in the winter. Minnesota, about this time of year, oh my goodness. One of the last times I was there, my parents live in Minnesota. Sleeping in the guest room, no night lights or anything. And I roll over and I'm like, did I just see like sparks? What the heck? I thought maybe I was just, I don't know, imagining things. But no, every time I rolled over, the air was so dry that there were little static electric shocks. In the pitch dark, I could see them. It was very freaky. Once I realized what they were, then I was able to go back to sleep. But yeah, it's crazy. Rub a balloon on your head. It builds up static electricity. So we've talked about these subatomic particles. Let's talk about protons. The number of protons that are in the nucleus of an element or of an atom define which element it belongs to. So that's like the identification of the element. So we call this the atomic number. It's given the symbol Z, which doesn't really make much sense to us, but it came from the German word Zahl, meaning number. So here we have a helium balloon, and inside the helium nucleus there are 2 protons. Every helium atom has 2 protons. 2 protons is what makes it a helium atom. Over here we've got a pencil with graphite lead, and inside the carbon are 6 protons in the nucleus. The atomic number. The atomic numbers for the elements are listed on the periodic table. Here's a nice one on the screen. We also have one always on display on the wall. So there's a lot of information in this periodic table, and we'll learn about it bit by bit. Right now we're focusing on this whole number above the chemical symbol for the element. The number 4 is the atomic number. That tells us the number of protons. So if I look at this guy down here, hafnium, which always makes me think it should be a Hobbit element or something. How many protons is in the nucleus of a hafnium atom? 72, because that's what it says on the chart. Okay, so the number of protons for all the elements listed on the periodic table. They're listed in increasing order of number of protons. So the periodic table is the way we choose to organize a lot of information about the different elements. So there's a unique atomic number and a unique chemical symbol. Now, you should be familiar with a whole bunch of those because I told you to memorize them. Chemical symbols have either 1 or 2 letters, The first letter is always capitalized. The second letter, if there is one, is never capitalized. It is important to make your capital and lowercase letters correctly when you're writing element symbols. For many elements, the first letter of the symbol corresponds to the first letter of the element name, but like with the letter C, there's a bunch of elements that start with C. And so then we had to add some second letters in there. So helium is HE, first two letters. Carbon is C, the first letter of carbon. Yep. That's an excellent question. So on our periodic table up here, let's see, is it on this one? So on this periodic table, it just shows some little asterisks over there. These were named a year or two ago. But on this periodic table, which is a little bit old, for number 118, it gives the name UUO. And this one's UUS. So those are man-made elements, and a bunch of scientists have to get together and agree when a new element is given a name. And so elements are discovered, and they're just given these names. These are, I believe, Latin names for 117 and 118. And so they're just like, okay, that's what we're going to call it until we decide what to name it. So excellent question. Some of the element symbols are a little strange, like Na for sodium. There's no N, there's no A in the word sodium. How did that happen? Well, some of the elements that were discovered early on have Latin names. So the Latin name for sodium is natrium. So Na is the first two letters of the Latin name. And so there's some that just, seem a little strange, like W for tungsten. Well, its Latin name was wolfram. So W. One of Dalton's principles in his atomic theory was that all atoms of the same element are identical. We now know that that is not quite true, so that was modified in the theory. What we know is that all atoms of a given element have the same number of protons. Every carbon atom has 6 protons, but they can have different numbers of neutrons. So those are called isotopes. Isotopes are atoms that have the same number of protons, but different numbers of neutrons. So if we look at the element neon, we find on the periodic table, there's a 10 above it, it's got 10 protons. All neon atoms have 10 protons. But some of them have 10 neutrons, some have 11 neutrons, and some have 12 neutrons. How do we know? Well, they tested some neon, and they found out. We didn't make that up, it's just observation. Because the protons and the neutrons are the massive particles inside the atom, a different number of neutrons is going to change the mass of the atom. So here we have 3 different atoms of neon, and their masses are not exactly the same. You might think that there would be equal amounts of all the different isotopes, that 1/3 would be 10, and 1/3 would be 11, and 1/3 would be 12 neutrons. That's not the case. They vary from element to element. And so we call this the relative abundance or the natural abundance of the isotopes. And that just has to be determined experimentally. What's interesting, though, is that natural abundance is quite constant. It doesn't really depend on where you got your sample from. You get a sample of hydrogen from Fresno, California, or from Cairo, Egypt, and the natural abundance of the isotopes is going to be the same. So we have to specify which isotope of an element we're talking about. Much of the time we don't care, but sometimes we do care, and then we need a way to identify it. drinking problem. So we use something called the mass number. The mass number has the symbol A. Not sure why. The mass number is the sum of the protons and the neutrons in an atom. So we can use a nuclear symbol that follows this pattern. The X here represents the chemical symbol for the element. And then we have stacked superscript subscripts on the left. The top is the mass number. The bottom is the atomic number. So here are the nuclear symbols for the 3 isotopes of neon. This has a mass number of 20, 21, and 22. They all have the same number of protons. Now, what's kind of handy about how that works out is if you subtract the lower number from the upper number, that gives you the number of neutrons. Because the mass number is the number of protons plus neutrons. So if you subtract the protons from the mass number, you get the number of neutrons. Another way to indicate what isotope we're talking about is using either the chemical name or the chemical symbol, and followed by a dash with the mass number. So we can call this Ne20 or neon 20. The mass number is the one that has to be specified. If we want to know how many protons it has, just look on the periodic table. But the number of neutrons is not given on the periodic table. So there's 3 isotopes of neon, and we look at the periodic table, there's no way we could figure that out. So here's a chart looking at, again, these 3 isotopes of neon, showing the number of protons, the number of neutrons, the mass number, and then this is the natural abundance, which is often expressed as a percentage. So 90.48% of neon atoms are neon 20. There's less than 1% neon 21 and 9.25% neon 22. These numbers come from observation. You're not expected to know those either. What you are expected to know is if I gave you this symbol, neon 20, or if I gave you this nuclear symbol here, you should be able to tell me the number of protons, neutrons, and the mass number, also the number of electrons that are in that atom. This number gives us the mass number, which is the protons plus the neutrons. The number of protons is available on the periodic table. So, a couple of questions here. What are the atomic number, the mass number, and the symbol for the carbon isotope with 7 neutrons? Well, what is atomic number? The number of protons, right? That's what identifies an atom as being a particular element. And that has the symbol Z. So for carbon with 7 neutrons, what's the atomic number? How many protons does carbon have? 6. So this atomic number is not going to change for the different isotopes of carbon. It's 6 protons. The mass number, well, might be helpful. Well, we can do that one next. The mass number has the symbol A, and that is equal to the number of protons plus the number of neutrons. So we already identified that this atom has 6 protons. How many neutrons? 7, because it said so. So 6 plus 7 is 13. So the mass number is 13. And then symbol. Okay, there's like 3 different symbols you could give. We could write the nuclear symbol. So we put the element symbol we just write that first. And then to the left, we put the mass number on top and the atomic number on the bottom. Or we can call this C-13 or carbon-13. Any questions? Yeah. Okay, that's an excellent question. So the thing that's the same is the protons and the electrons. Protons and electrons in a neutral atom are always the same because that's the only way you can have a zero charge. Because the neutrons don't have any charge, you can throw some of those in or take some out, and it's not going to affect the charge.
Okay, so then there's going to be 6 electrons.
There would be 6 electrons. Okay. Yep.
So we basically just when it says carbon, isotope, we look at the element and then we just do the math.
Yeah, you find the atomic number from the periodic table, and it's going to have to give you some indication about what isotope it is, and then you identify that and you just do math. It's just very simple, adding, subtracting, right? So let's look at another question. How many protons and neutrons are present in an atom of potassium-39? So here it's asking for a number of protons and neutrons. Well, how many protons do all potassium atoms have? 19. How many neutrons does this particular type of potassium have? It's going to be 20. Well, how do we know that? Well, this is stacked up for subtraction. That does not mean that you can't use your calculator to do that, because some of us are a little rusty doing simple math in our heads, and I don't care about that. I just want you to get the right answer. Okay? So 20 neutrons. How many electrons would there be? 19. Because there's 19 protons. Electrons and protons in a neutral atom will always be the same in number. Because here we have a positive 19 charge on the nucleus, and so we need negative 19 charge in the electron cloud so that the atom is neutral. So in a neutral atom, the number of electrons is equal to the number of protons. Number of protons is called the atomic number, Z. When chemical changes occur, when chemical reactions occur, atoms can gain electrons or lose electrons. And when they do that, they become charged, right? And we call a charged atom an ion. So if it has a positive charge, like Na+, it's called a cation. This is not an abbreviation for vacation. It's not cation or cation. Cation. Cations are positive. You need to remember that. Negatively charged ions, an example here is F-. Fluoride is an anion. So anions are negative, cations are positive. If you like cats, this will work for you. I have positive feelings for cats. Cations are positive. If you don't like cats, that's not going to work.